I'm sorry you had to see that. I was locked out and trying to get in, but I guess there's no chance of me getting in without a key. Or is there? Quantum tunneling is a phenomenon which states that if a particle were to interact with a barrier possessing a high energy, meaning that it's stronger than the particle, even though normally we would think that it would rebound, there is a chance that the particle could end up on the other side of the barrier. But how exactly is this possible? To make sense of this, we first must understand a very key concept that is constantly used in quantum mechanics, the Schrödinger equation. In the quantum world, all particles are described by what we call wave functions, and Schrödinger's equations describe the wave function of individual particles. So if the particle is represented by a wave, it could be in multiple locations simultaneously, right? Yes, exactly. The probability of a particle being in different locations is given by the square of the amplitude of the wave function. So the particle is more likely to be there than the two smaller amplitudes. Let's say that I'm a particle. Due to my surroundings, I'm more likely to be in certain locations, especially where that ice cream is. But there is a chance of me being in other places also. But more frequently, I appear where that ice cream is. This can also be stated by saying that I'm in all possible locations at the same time. But how do we know a particle's exact location? Well, a particle can exist in a variety of states at the same time, and we call this being in a superposition of states only when it is not observed. But once we observe that particle, it collapses to a single location. Let's see how this looks like in a graph. On the x-axis we have the position, and on the y we have the symbol representing the wave function squared so that we can get a probability density. Let's say that the graph looks like this. If I want to find the probability between A and B, the area under the curve would represent the probability of the particle. But what would happen if I observed the particle? Well, the wave function would collapse into a delta function with a single spike at the observed value. However, the area under the curve between negative and positive infinity of the particle should equal 1, meaning that all possible states of the particle should add up to 1. Relating this back to quantum tunneling, let's say that there is a particle approaching a barrier and the particle is represented by its wave function. As it slowly approaches the barrier and hits the barrier, its wave function decreases exponentially and appears out on the other side. It is important to note that the amplitude of the wave function never truly reaches a value of 0. That's why there is a chance to find the particle on the other side of the barrier.
Thanks for watching.